Technology, Bombay, in probably that year is not here, and his area of research is synthesis of functional oxide nanomaterials, magnetic and multiferric materials, bulk and thin films, and understanding of their physical properties like structural, electrical, magnetic, and optical, study of laser production, plasmas, and pulse laser deposition of thin films. Presently, he is working as a head of department of physics here in MNNIT under his dynamic leadership that we are trying to have so many to start the other courses. And he is a very dynamic fellow and having many assignments. That is at present he is deputy dean of this faculty welfare, deputy dean academic, coordinator TQ, warden, and so that is a very big list that I am having. And he has supervised 7 PhD students, and 4 students are working at present. He is having a very good publications in international journals, and all his publications they are well cited. So I can say a lot of things about him, but due to shortage of time, I am unable to do that one. So with this brief introduction, I invite Dr. Naresh Kumar, and his topic of the lecture is pulse laser deposition, oblique ablation, synthesis of nanomaterials and thin films for energy storage. So over to Professor Naresh Kumar.
Namaskar, sir. Thank you so much. Firstly, namaskar to everybody. Am I audible?
Yes, you are audible. You are audible. Please go ahead.
Let me first thank Professor S.N. Pandey for such a long introduction, although he is saying it's a brief. Thank you so much, sir. And secondly, I must thank Professor S.N. Pandey for giving opportunity to present my small, research work here in this FDP. One thing I need to declare before I start with this lecture, because indirectly I have been associated with the topic, but actually I don't work with energy storage materials. Okay, that's my one declaration. But I tell you one thing: the kind of technique or the tools that we have been using, they are useful, and there had been significant reports suggesting that yes, this tool or technique can also be used to prepare materials or devices for energy storage. I will cite one or two or maybe some examples where you can find the system useful, right? So my topic of presentation is not exactly in the energy storage, right? You might have heard many lectures since the starting of this FDP. So I will not be teaching anything in energy storage related issues, but I would be discussing some technique or the tool which can be used to synthesize or prepare materials or maybe the devices for your demanding applications, right? So that's my small declaration.
Professor Kumar, your lecture that will be more beneficial because we are having many lectures on energy storage.
That's what I'm saying.
And that's why it will be very, very
so let me see.
Interesting for us.
Yes. So I would be discussing almost every point, every aspect of the tool or the technique. And if you have any question, you can interrupt me in between, or you can raise questions towards the end of the lecture. So that's an issue. Okay. So I know there is a long list of participants attending this lecture. It's a big list. So now let me share about more than 70 participants are here, and I think most of them are faculty members. Okay. So let us see, how I can go ahead with that. So I am sharing my screen right now. I hope my screen is visible.
It will take some time. Yeah. Yeah, now it is visible.
ठीक है sir. So as sir has said, my topic of discussion is pulse laser deposition or ablation. So I would be discussing more on what exactly is this technique, okay, and then how to. I will discuss almost all possible details of it, and then I will discuss certain examples where you can make this technique useful, right? Let us have a small plan. I would be talking about introduction of thin films that I think many of you know, but let me just quickly run through what exactly I mean by thin film. Then I would be discussing PLD, pulse laser deposition, or pulse laser ablation. There are many terminologies used. So we will accordingly move ahead. So I would be discussing more on pulse laser deposition part. Then towards the end of the talk, we will be taking certain examples that we have carried out at here, certain experiments, certain results of our own, and there are certain results from some other researchers. So I would be discussing all of them. Okay. So I think one may ask question, okay, why do we study thin film, or why do we prepare thin film at all? You know, that's a very simple question. Why do we deposit thin films? Why do we study thin films? What is, why they are of interest? So there are many, this question, we can have different answers, or rather there are many possible answers. The first answer that I would like to mention is, okay, the moment you synthesize thin film of any material, their properties, when I'm saying properties, I'm talking about its physical properties, meaning thereby maybe structural, magnetic, electrical, electrochemical, okay. So all these properties might be different from their corresponding bulk counterpart. The reason might be, it's a volume to surface to volume ratio is one reason, or there are listed reasons here. Why it is because the grains of the thin films are different from the bulk counterpart, and another reason might be the film may not be fully dense, okay. Yes, since we are making these films over some material which we call as substrate, so the moment we deposit films on substrate, films might be under stress. The stress might be of any kind, right? And then the defect levels, defect structures might be different from the corresponding bulk counterpart. And the next is very important. They are strongly influenced by the surface and the interface effects. Those are coming from the substrate. Here, in case of thin films, my substrate on top of the thin film is basically deposited, plays very, very important role. So when the moment you start looking at thin film of any material, one very important parameter one has to look at is what is the substrate on which we are going to deposit these films, or the thin films of that material. So based on the choice of substrate, my film can be polycrystalline, it can be epitaxial, it can be highly oriented, or you can, in fact, sometimes you can generate stress of different level. And accordingly, their applications might be different. So these are few issues that one should look at with regard to the thin films, right? Now, based on the properties, my thin films may have different applications. Almost in every area, you will find, yes, there are applications. Some of the slides maybe you might have, okay, that's fine. So I'm just discussing a few examples. Like when I look at the transport, electron transport, the moment I go from bulk to thin film, there is a change in resistivity, or I would say there is an increase in resistivity. For example, if you deposit thin films of metallic material, yes, their resistivity may go up, or it may change. Corresponding applications might be resistors based on thin films. Similarly, when I talk of magnetic materials, yes, there are abnormal changes, abnormal, I mean, I would say there is a huge increment in magnetic properties when you synthesize thin films of magnetic materials. Examples I will cite that a material, if a material is non-magnetic in bulk, it may be magnetic in thin films, right? Coercivity you can tune as per your demand or as per your application, right? So thereby there it has many applications like magnetic storage, magnetic memory. Similarly, superconducting material, if somebody is looking after superconducting material 1, 2, 3 or any other, then once again it has a tremendous application, right? And application, one of the common application is on device. Similarly, in optics, if I look at optics, the reflection and absorption, it is depending, right? So accordingly, you can have applications in AR coating, anti-reflection coating of glass, right? Electrochemical reactions, it is of your interest. I think ionic conductivity can go up, and accordingly, energy storage is one more area of interest or concern, right? So these are a few applications where we can make use of these thin films, right? Now the next question comes, how or what are the different modalities or modes through which my films can be grown? That's a very common picture that you might have come across because it's already there in the textbooks or in different standard literatures. So there are three possible film growth models. One is island model, second is layer by layer growth model, third is mixed growth. So when I talk of island model, it's basically from three-dimensional islands. Here, important thing is film atom, okay, the atom, they are strongly bound to each other as compared to the substrate, right? So they first have binding with them, then with the substrate. Okay, there is a slow diffusion here, and accordingly this kind of growth is done. Second is layer by layer. It shows very good crystalline quality, but here the interaction or the binding of the film atom with the substrate is more as compared to among each other. Third one is the mixed growth, where firstly you have layer by layer, then the island growth is done, right? So these are different modes. If somebody is interested in, one can go through the details of these different growth models, right? So that is how we can grow thin films. Now the issue is, what are the possible methods through which one can synthesize, one can grow thin films, right? Basically, I would divide growth into, the growth of thin films by two different prominent methods. One is chemical vapor method, or second is physical vapor method, CVD or PVD. Other than that, also we have few systems that I will be just listing them. It's just informatory. I'm not going to detail on it. So if I talk of chemical vapor deposition, in CVD, you need to have reactant gas. So within the chamber, one has to have reactant gas. So this reactant gas, when it is introduced in the chamber, chemical reaction will occur and you will have deposition of solid films on the substrate that you have kept in the chamber. Examples are atmospheric pressure CVD, low pressure CVD, plasma enhanced CVD, metal organic CVD. Okay, so these are mostly used for dielectric and silicon or semiconducting related thin film depositions. Then the second is physical vapor deposition. Here no chemical reaction is involved, and here what we do is we try to create plasma. Okay, we try to create vapor of constant materials inside the chamber, and then we allow them to condense over the surface of a substrate, which we call as a vapor or the substrate, and accordingly we get a deposition of a film finally, right? And there are again various techniques, various instruments, various techniques which may be kept in this PVD category. Thermal evaporation is very common, where you try to deposit thin films of any metallic material. So if somebody is interested in preparing electrodes of any metallic material, for example, platinum or copper, then thermal evaporation is very important. Similarly, electron beam evaporation. So you take an electron beam and try to evaporate material, and then you deposit thin films. So sputtering is the next. Okay. Within sputtering, you have RF, radio frequency, or magnetron or DC. So based on your availability and the requirement, you can go for sputtering as well. And then we have got pulse laser deposition. This is one among them. And then molecular beam epitaxy, which is one of the most expensive technique, right? So based on your materials or the area of interest, you can choose these techniques. Every method has its own pro and cons, I would say. For example, if I talk of molecular beam epitaxy, one of the best technique to, or the best technique to deposit or grow high quality thin films, but it is very, very expensive, right? This is one drawback. Okay. Similarly, PLD, it is again very good technique to grow high quality films, but it has certain disadvantages. For example, I mean, if you want to grow large area thin films, perhaps a bit difficult, but I will be discussing all those issues in this PLD in the method. And if I talk of sputtering, sputter deposition of thin films, there it is commercially available method. Okay, but there is a problem to have sputtering or to grow films by using sputtering. You need to have a bigger target, and that requires a lot of efforts to make target, right? So similarly, you may find certain difficulties, certain advantages or disadvantages associated with different techniques, right? Other than that, other than these two categorized techniques, there are other methods as well. I think one can go for coating with liquid. Okay, then you can go for electrodeposition. That's very simple, very commonly available. Spray paralysis, another very spin coating, dip coating. So there are various methods available for the deposition of thin films. These methods are very, I mean, I would say cost effective. They don't cost much. Spray paralysis is a very simple method where you try to make spray, okay, and that spray of the constant material goes and sits at the substrate and accordingly it forms thin film. Similarly, electrodeposition, you basically do the electrolysis and finally you have a film of material. So for electroplating, this is basically used. So there are, I mean, techniques which are other than this CVD and PVD, and those techniques are cheaper and one can easily handle those instruments or those techniques, right? So now among all these, so list is very long. So among all this, I have chosen one method which is pulse laser deposition. So this method I shall be discussing here. For the growth of thin films, one important or prominent application of it. Second is one can also synthesize nanostructures, nanomaterials with the help of pulse laser ablation. So I will be discussing something on this also. So now this slide is coming suddenly in between, but it's okay. When I'm synthesizing film or thin films, there are definitely few issues that one should look at. And if you could address all these issues, perhaps you can grow high quality thin films. You choose any technique of your choice. I mean, depending on availability and requirement and applications. But finally, one has to look at certain issues which are related to the thin films. Stoichiometry is one. What do I mean by stoichiometry? See, when I'm synthesizing film of any material, it has to have same chemical composition, right? So my chemical composition should not go off. Next is, if I am interested in growing high quality oriented thin films, then one has to look at epitaxial growth. And for epitaxial growth, one has to choose substrate wisely. If you cannot do that, then perhaps you will not be able to grow epitaxial film. Then next is impurities. So if you are trying to grow films, and that too at, let's say, very high temperature, let's say more than 800 degrees centigrade, or sometimes even 500, more than 500 is also assumed as high temperature. Then in that case, there is a chance of having impurities, either they are coming from the substrate or maybe coming from some other nearby sources. So one has to look at these impurities also. And accordingly, if I'm looking at this, then one has to be very, very careful on impurity portion. Otherwise, you will be claiming that this property is coming because of material or the film, but actually it is coming from impurity. For example, if I am depositing zinc oxide thin film, right, and if there is a magnetic impurity coming in zinc oxide, then my zinc oxide thin film will show you magnetization, and you will claim, sir, my zinc oxide film is magnetic in nature. Although there have been various reports, reasons might be so many, but this is one case where one has to be very, very cautious. Okay. Next is strain. So when we deposit films over a substrate, usually the crystal structure of the substrate and film are not same, and accordingly my film can be under stress or strain. So one has to look at this also. And secondly, and the last is, there may be a few more issues also. And the next is, second phase means, let's say I'm trying to grow film of multi-component, multi-constraint materials, where ultimately it has to have just one phase. But during growth, I don't know what had happened, and you start getting different phases, multiple phases. That's another problem. Next, and one more thing is, I think I'm just going ahead with this. There are certain more issues like uniformity. Based on the technique or the tool that you are using, it may be possible that my film is not uniform, or the thickness is not uniform over the entire given area. One more issue is the surface quality may not be very good. You may have many, roughened surfaces, right? Roughness is not very, very good. Film surface is not very much smooth. Okay, or sometimes the film is not very well stick to the substrate, so it is getting peeled off. So adhesion with the substrate may not be very good, right? So there are plenty of issues that one has to look at before you jump into the business of, I would say, thin film growth or study of thin film of any material. So one has to look at all these issues. Perhaps then I think one can finally grow or deposit very high quality films of desired physical properties or desired properties, I would say, right? So these are certain issues that one should look at. I'm now going ahead with the technique that is very important, very, very useful for the growth of thin films. And it is called as pulse laser deposition, or PLD. So in PLD, if I just say PLD, it's a very simple technique. Okay, you take a laser beam, you just take high power laser beam, and you focus it to a material. So that material will absorb optical energy or the energy of the laser beam and will create a plasma. That plasma will finally expand and will sit at the surface of the substrate, right? And you will have a film of the material grown. So that's a schematic. Let's say this is this chamber, and here in this chamber, let's say this is my, these are 1, 2, 3, I can see 1, 2, 3, this kind of thing. These are basically ports. These are basically, I would say ports where you can hold target. Target means it is a target of which you wish to synthesize thin film, right? Right. Opposite to these targets, there is one more assembly here. We are calling it substrate heater assembly. So here we have a provision of mounting substrate. I am calling it substrate heater. So that means we are mounting substrate on a heater. That means during deposition, if you are willing to grow, if you are willing to provide temperature, that you can easily do with the help of heater. It is your choice. If you wish to deposit at room temperature, you can do. There is no need of giving temperature. So this is the substrate. This segment is basically substrate heater, or I call it substrate holder, right? And opposite to it, this is basically the shutter. Okay. So if you don't want deposition to occur, you can close the shutter. Here I'm showing 3. If you look at target holder once again, I'm showing you 3, 1, 2, 3 holders. So these are basically meant to grow multi-layer thin films. Let's say you have 3 materials, and if you wish to make thin films of 3 different materials or multi-layer of 3 different materials, then you can make use of it. Otherwise, also you can use 2 different target to make thin films of one stoichiometry, right? Rest other, these are the ports from where we can actually see the system, what is exactly happening here. We can allow gas to get in, and some of them are for vacuum, creating vacuum, and maybe for some other probes. If you wish to, let's say if you are willing to analyze a plasma, you can have some probes inside the chambers, so that is there. Now, what happens here is you have a laser, it's a high power laser, right? So we take high power laser. I'm taking neodymium, yttrium, aluminum garnet laser, which is commonly known as NDR laser. So laser beam is coming out of it. We focus it with the help of lens, and this focus beam is being incident on a target, and finally you have a plasma, and this plasma expands in vacuum, and finally you have a growth of thin films at the substrate, right? So this phenomena looks very simple, right? You just take a laser and shine it to the target, that too in a chamber, and you will be having a thin films growing. So the system looks very, I mean, the process looks very, very simple. But I tell you, although it looks very simple, but it has lot many variables, it has lot many parameters, and controlling of all those parameters is really difficult, right? But if somebody has optimized the parameter, then life is very simple. And since this system has lot many process parameters, so you can control growth of films based on different process parameters, right? So I would be discussing one by one all those parameters. Here I am showing you what exactly is happening in the chamber. You see, there is a blue colored, I would say, plasma here. So that means laser beam is coming and it is striking at here, from where plasma is coming out. And this red segment, it is basically the heater. It is the substrate heater. So where we have kept the substrate. So when a laser hits a target, so there is a laser target, laser material interaction. So in that case, my electromagnetic energy, which is there with the laser pulse, it is converting into electronic excitation within the material, and then into the thermal and mechanical energy that causes ablation. And during ablation, what is happening? A kind of plasma is coming out. That plasma has atoms, molecules, electrons, bigger particles, clusters. So they all will move ahead, and they will sit here at the substrate. So that's what is exactly happening in pulse laser deposition, right? That's a very beautiful picture I'm showing. We have got PLD set up at this institute. So there is a high power laser. This is quanta system high power laser, and we have got one chamber here. I'm sure I will be showing what is the use of these two chambers. So there is one chamber here. This is one more chamber. Basically, this chamber is it is connected through diffusion pump. So there is a DP based vacuum chamber, and this chamber is basically turbomolecular based vacuum chamber. So for two different type of materials to synthesize, we have been using these two chambers, and these are the chambers used at different places. So one more thing, it is not necessary that your chamber has to be spherical, right? Kind of spherical ball. Here I am showing you a spherically symmetric chamber. You can have cylindrical chambers as well. So there is one more chamber where its structure is not spherical. Okay. So maybe let me just show you what exactly are the components here, if you are interested in. My laser beam will come somewhere here. I'll discuss that also. Will come somewhere here. This particular section, you see this particular section, it is my target holder assembly. It is my target holder assembly. And here it is my substrate heater assembly. In this target holder assembly, you see there is a kind of scale here. It's a kind of motor, I would say. It's a stepper motor connected to the target holder. So during deposition, my targets are being rotated, right? Otherwise, my target will melt, okay? And we won't get deposition there in the chamber, okay? And this is a gate valve which is used to control pressure within the chamber. These are fans. Here it's a target substrate heater, I already said. And these are the ports. So that's open port. This is view port. This is also view port. right? So these are the different ports from where you can actually see what exactly is happening in the chamber, right? Here again, this is the viewport. This is my target holder opposite to, this is, sorry, my substrate. This is here in this is my substrate heater port, and opposite to this somewhere here is my target heater port. Again, this is the viewport, this is also viewport. If you want to add some more probes into it, you can make use of these probes, right? Ports. Okay. What happened? Yes. So let us look at segment of this system one by one. You know, when I talk of substrate heater, I told it is not a holder. It is not a place where you actually hold your substrate. So let's say this is actually a picture of substrate heater or holder, I would say. So this heater has arrangement of heating it. So there are coils, and again you can control the temperature with the temperature controller. So this is the top surface of substrate heater where you actually mount your substrate. So this is substrate. Here I'm showing you silicon substrate of about 1 centimeter by 1 centimeter area. Okay, so this is mounted over this substrate holder or heater. And for mounting these substrates, there are two ways of mounting. You can either use epoxy, okay, silver paste or any conducting paste, okay. Otherwise, you can make use of these clamps. You can make use of these clamps. So, you know, since the whole system is getting inside the vacuum, so during deposition, you cannot do anything to it. Okay, so one has to be very careful while mounting substrate at this heater or holder. Why? Because let's say if this substrate is not mounted properly, then what may happen is that during deposition or during vacuum, it may fall down, and you need to once again open the chamber and again mount the substrate. So mounting of substrate is very, very important here. This is one thing. There is one more important thing. Since my plume or the plasma is directional, this is one, I would say, drawback or disadvantage of PLD. What happens is my plasma is basically directional. So it will be focused, it will be directed to a region. So what I did is, before mounting the substrate, we did a test run kind of thing. So we just tried to deposit plasma on the entire substrate heater, and we will see the reason where my maximum plasma is coming. So maybe here is the reason where majority of plasma is coming. So what I will do, I will try to place or fix or mount my substrate in this region. If I, let's say, mount it here, perhaps my film growth may not be good, and uniformity of the film thickness may not be very good. So one has to be very careful about it. So there are two important issues at here. Number one, my substrate has to be mounted properly, otherwise it may fall down. Secondly, I need to mount this substrate in a region where my plasma is uniform, so that my thickness of the film is uniform. Otherwise, uniformity of the film thickness is a very critical issue in PLD. Okay. Then next is, you know, in PLD, as I said, laser is very, very important tool, and not only important, it is one of the most expensive part of the PLD. So if I talk of, let's say, this is the solid state laser. Here we are using Nd:YAG laser. So Nd:YAG laser cost, as of now, I think it would be costing close to 40 lakhs, right? But if I look at excimer's lasers, gas lasers, they are more expensive than the solid state laser, but they are better in terms of stability, right? So based on your funds and applications, I would say you can choose lasers. But yes, solid state laser with all possible wavelengths starting from IR to UV. So 1064 is its fundamental mode of Nd:YAG crystal, and if you take second harmonic of it, it is 532. If you go for third harmonic, it is 355 nanometer. If you go for 4 omega or the fourth harmonic, then the wavelength which is coming out from the laser is 260 nanometer. So based on your application, you can choose any of the wavelength in this Nd:YAG laser. However, if I go for excimer lasers or gas lasers, they have fixed wavelength. For example, if I go for xenon fluoride, then it has a wavelength of 351 nanometer. So if somebody is interested in working with this kind of wavelength, then one should go for this. But these lasers are a little expensive, right? And they need gases. So there is a frequent consumption of these gases, xenon fluoride, argon fluoride. So these gases are expensive, and one has to be, ready for consumption of these gases. However, in case of solid-state laser, there is no such issue of consumable. Yes, after some time, after a few million shots, maybe flash lamp requires to be replaced, but that's not very expensive. I would say about $500 you can have a flash lamp. So that's one important thing I wish to share. Now, so I said that there are two important parts of it. One is this chamber, this laser. Second is the chamber. And chamber has, as I said, heater is very important part. So I have shown it. And others are vacuum components. If you have funds, you can use turbo molecular pump. Otherwise, initially I started with DP based PLD chamber. Then later on we could add up to a chamber with turbo molecular pump, right? So that's how we can have a PLD system. Now let me look at why we are going for PLD. What is the beauty of this pulse laser deposition system? You know, one of the very important advantage of this PLD is it is a very versatile method, and in this method almost any type of material can be ablated. You can create plasma of any type because its laser energy fluence is very high. Okay, this is one thing. Second, it's a congruent evaporation, and accordingly you can maintain chemical, which was one of the very important issue in thin film growth. So chemical stoichiometry can be maintained, particularly in a system where you have got multi components. For example, if I'm looking at superconducting oxide, for example, YbCO 1, 2, 3, 4, right? So there are multi components materials multi components are there. So in order to maintain chemical composition, because in that superconducting material 1 to 3 4 ratio is very 1 to 3 ratio is very important. So one has to be very careful about it, and PLD helps in that. Okay, so chemical composition is maintained nicely with this PLD. So one growth issue can be handled with the help of PLD very easily. And one more thing is multiple use of laser. Laser, as I said, it is one of the very most expensive part of this system. So you can, not all the time this laser is being used. So whenever you are depositing film, you are using it. So you can keep this laser outside the chamber, and you can use this laser for some other application if you wish. So if somebody is interested in making use of laser for different applications or diverting beam for some other chambers, one can easily do that because it is not lying inside the chamber. And the next, I personally feel this to be a very important advantage because in PLD, the size of target is not very big, about 15 mm or 1.5 centimeter diameter. Target one can easily use for the growth of thin film. Thickness can be of any type. So one can make such a small target easily, one thing. Secondly, to make target, you require high quality or high purity oxide or powders, constant material. And high purity constant powders are expensive. So if you are preparing target of smaller size, you need small volume, small mass of the such expensive material. So that way your cost is going to be nominal. Not nominal, but yes, if you compare it with the sputtering where target size is of 2-inch, diameter of 2-inch or more. So preparing target of 2-inch diameter is technically difficult, and it requires more of powder, more of material, which is expensive. Okay, and it is consumable in nature. So you every time if you are trying to experiment with different type of targets, then with sputtering it is little limited. Okay, but with PLD you can easily do that. So this is one very important benefit. And here we are saying the fabrication of multi-layer is straightforward because you can have 5-6 in our system. We have got 6 arrangement of mounting targets, so you can mount 6 different targets at a time, and accordingly multi-layers of 6 different target can be grown easily. I think it's not listed here. Maybe epitaxial growth can be easily done with the help of PLD. So if somebody is interested in growing epitaxial film for particular application, then just choose the substrate for the epitaxial growth, and based on the optimized process parameter, epitaxial growth of thin films can be easily done. Okay, and yeah, these are few advantages of PLD. Now let us look at many such issues that I said. Here I am saying this is a versatile method. What do I mean by that? Versatile means, as I said, almost any type of material can be used. So what is happening? When this light is, when the laser beam is made incident at the target, you know, there is a very high electric field inside the material. So this electric field is being generated inside the material. And the strength of this electric field is 10 to the power 6 volt per centimeter. And this electric field is very, very high. And this is more than enough, or it is sufficient to have dielectric breakdown. And accordingly, one can create plasma of almost any type of material. So that's one thing. So if you want to grow films of thin films of any oxide insulating material, it's very, very, very simple, right? Next is congruent evaporation. So that is how your stoichiometry is maintained. So you have got a laser beam coming in, right? And it is being absorbed by the material, target material. Now what is happening here, non-equilibrium heating by the laser beam, it is producing a flash of evaporants. And this flash of evaporant is going and it is sitting at the substrate. And the moment it sits at the substrate, the composition stoichiometry of the film is exactly same as that of the target. And you know, this is the condition for which my congruent evaporation can take place, where L is the heated thickness, ED is the evaporated thickness. Just do take care of it, and it is done. Next, I said multiple use of laser. I was telling, let's say you have got one laser here, laser beam is coming out. So what you can do is you can have beam splitters. You can split one beam into multiple. Let's say here you have split it into two. One beam is coming from here and there is one beam going straight. So this straight beam, you can have one more beam splitter here, and accordingly you can have different chambers, and you can divert the beam to different chambers, and accordingly one laser can be used in multiple chambers, right? So that's one very important use of laser. So after spending such a huge money, my laser can be used for multiple applications. Okay, this is one very important benefit of this system. Here, that's how we have done. There is a laser coming up to this mirror. So this mirror is diverting laser beam to this one more mirror. So we have got one more intermediate mirror here. So if we wish to take my laser beam to this chamber, so what we do, first laser beam is at here, then it is reflected to this intermediate mirror. From here, all are mounted at 45 degrees. So from here, it will be reflected to this chamber. And if I'm not willing to use this chamber, I will take this this mirror out. Okay, I will take this mirror out. So if I take this mirror out, laser beam will go up to this third mirror, and from there it will once again reflect, and it will go to this chamber, which might be used for some other growth of the thin films, right? And not only that, if somebody is interested in growing nanomaterials of the thin films, yes, you have got laser beam out. Just make use of some more mirror and divert it to the system where you can grow nanomaterials with the help of laser. So that is also very easy. But I tell you one thing which is very, very important here. Okay, these mirrors are not ordinary mirrors. One has to be very careful about. These mirrors are not the ordinary glass mirrors, because here my wavelength is very particular and energy of the beam is very, very high. So accordingly, we need to choose these mirrors. Mirror means coating of the material, which will act as a mirror. So for a particular wavelength, I will be choosing a particular mirror kind of thing, and that mirror is again expensive. So the setup is a bit expensive. Okay, so if I'm using 355, so I need to use mirrors accordingly. If I'm using 532 nanometer, then I need to choose these mirrors accordingly, right? Mirrors are very important. Now, when the beam goes inside the chamber, as I said earlier, we need to use we need to focus this laser beam, and for focusing laser beam, we need to use this thing, lens. So that lens is not an ordinary lens once again, right? So we would be using fused silica lens, quartz lens, right? So again, bit very careful. One has to be very careful about these optics, right? अच्छा एक चीज और है, maybe towards the end I will tell. Um, Once this arrangement of reflection is set up, is done, one should not touch, one should not disturb it. So one has to clamp the whole uprights. Otherwise, if this position of these mirrors is changed little bit, then what will happen? My laser beam will go to some other place, and I will not be able to focus the beam at the target, and I will have to struggle a lot for getting deposition or getting plasma, right? These are few good things about PLD. There are some issues also. One has to be careful about these difficulties. I'm saying difficulties, not the problems, because these difficulties can be minimized or can be overruled up to certain extent. So I will be discussing those also. Here, splashing of micron size particle is one of the major problem in PLD. What is splashing? When I talk of okay, anyway, so splashing means bigger size particles are coming in the plasma, and they are getting deposited over substrate along with the plasma, right, along in the film. So my roughness, my surface quality of the film may not be very good. So I told earlier also it is one of the growth issue. So this issue is there with this system, but there are ways of minimizing it. I will be discussing those also. Next is small area of uniformity. In the PLD, because my plasma is highly directional, so the thickness of the film uniformity is an issue. Okay. Next, non-conformal coverage, same thing I'm talking about. Okay. One more thing, okay, what exactly is happening during the film growth? The theory or the physics of it is very complicated. So there had been different experimental methods where they take probe, Langmuir probe they take, and they try to analyze the plasma. They try to look at what exactly would be happening at the time of growth and how one can control properties based on the plasma, or how my properties are governed through this plasma. But this theory is little complex. So one experimentalist usually, he doesn't go into that area, right? Next is, which is very important, growth temperature. In PLD, usually, if I'm working with oxide films, they will grow, or they will take their structure or crystal structure with the desired magnetic structure or other properties when they are grown at high temperature, right? So growth temperature in PLD is one more issue. So these are few issues I shall be discussing all of them one by one. So let us look at splashing. So what is happening is splashing. When I already mentioned in PLD, in plasma, I am getting bigger particles. It's a SEM, scanning electron micrograph of the thin film. We are getting particles of almost micron size. So these are the particles. In the surface, I'm getting very big particles. And since it is an intrinsic problem in PLD, because my energy is absorbed quickly, so sometimes from the surface, there are various reasons for it. So it's a kind of intrinsic issue. So yes, it is there in the PLD. So if somebody is willing to have high quality films with no bigger particles at the surface, then PLD is very difficult. One has to look at this carefully. But yes, it can be minimized, it can be reduced up to so much extent. Ways of minimizing, I think this is the method, that's how my splashing is done. You have a laser beam coming in, and then you have molten globules coming in. So they will hit at the surface, and maybe here cone size of material is left, and from here my randomly shaped particulates or bigger particles will come out, right? So that's a mechanism. But yes, I can minimize. These are few examples where we can minimize this splashing. One very common method of minimizing splashing is, okay, do not go for perpendicular on-axis PLD. On-axis means do not keep your target substrate exactly opposite to the target. Rather, you place it at a off-axis, right? So, for example, let's say I am having a target here. This is a target, so laser is coming up to here. So instead placing my substrate opposite to it, let us place it off axis. So here my the quality of film might be better, and you won't get the particulate, the bigger size particle coming and sitting at the substrate. This is one way of minimizing it. Other way, there is one more way of doing it. You should use target. You should use target. Target means the material, or the material from where you are going to create plasma. So that target has to be of very high density. So try to make target of maximum possible density as you can. If it is brittle, if it is not dense enough, then this problem will be more. So one thing is, try to make target with maximum possible density. Now it is you to take care of it. One more thing, one more way of doing it, minimizing it, before every deposition, just take out the target and polish. Make use of polishing paper, fine polished paper, and polish it, so that the surface of the target is smooth. If that is happening, then perhaps you can minimize surface up to so much extent. I'm showing you my own work of very high quality thin films grown by using PLD, and it has very good surface, right? You see, it's a terbium iron garnet film, very uniform thickness. Okay, thickness is very uniform, of about 250 nanometer. It's a cross-sectional SEM, and if you look at atomic force microscope, I don't see any bigger particles at the surface over this 500 nanometer area, right? Even for larger also, I don't see. Yes, there are some particles over the larger area, but it was much better than, and it is acceptable for my own applications, right? This is one way. Next problem is small area uniformity is an issue, because my film, the area of the film is not uniform. More area of the film is not uniform as far as thickness is concerned. The reason is my plasma is directional. So if you are exactly opposite to the target, then the thickness has to be very high. As you go off from this axis, let's say theta is the axis, then thickness is greatly depending upon this theta, and the relation with the thickness and the theta is cosine to the power 11 theta. So with a small change in angle, so if you are at here and if you are at here, maybe thickness would be drastically changed. So we have shown, it has already been shown that as a theta is increased, thickness has been gone down to lot much extent, right? So one has to look at, or has to be very careful for large area uniformity. So that is why commercialization or commercial application of this PLD is restricted. Okay, so for cost-effective production of thin films, this method is not recommended, and accordingly, it is not industrially acceptable, right? However, if I compare this method with sputtering, their deposition over large area is very straightforward, and that is why it has been commercialized, right? In all commercially thin film industries like CD or hard disk, their sputtering is used commercially, right? But yes, there are ways of overcoming this issue also. One can minimize, one can take care of this uniformity issue as well. How to do it? During deposition, one thing is I'm rotating target, but what you can do is you can rotate substrate also. So, and that rotation has to be rotational as well as, I mean, it's a movement of substrate. So you can move substrate translationally as well as rotationally. So in the entire area where my plasma is coming in, you keep moving with a constant rotational and translational motion. And if you could do, then yes, you can grow films of uniform thickness over a large area. That one can easily do. Not easily, but yes, it has been established. So like if you see here, we have, I mean, it has been shown that films, if you rotate the substrate heater or holder, then thickness over 8-inch area is about 4%. So that's how it has been shown, right? So thickness from here to here, it is 4% over 8-inch, means from one end to another end, thickness is 4%. And if you go for 6-inch substrate, then it is about 1%, provided if you are rotating substrate heater during deposition, right? This is one good way of controlling thickness. Then other than the difficulties, or I would say good thing about PLD, there are some parameters which are also very important and one should look at. Here, since laser is coming and it is being focused at the target, so laser is basically laser has its energy. So this energy is falling at a certain area. So laser energy falling per unit area is basically per unit area per unit pulse or per pulse. This is my laser fluence. So basically in per pulse, how much amount of energy is being transferred to the target will decide whether my plasma, we can create plasma or not. So here laser fluence, which is basically laser energy per unit area per pulse per second, is very important, right? So this since I'm saying laser energy per unit area, if I'm let's say my let's say pulse width is same, let's say I wish to find out laser fluence or laser energy. Laser fluence is my laser energy per unit area. So here, let's say 200 millijoule is the energy. And if my area is smaller, my energy fluence will be higher. If my area where my laser beam is falling is higher, then my energy fluence will be low. So if you want to have optimized laser fluence, one has to take care with my spot size, laser, I mean the area of the laser beam. Why? Because the laser beam which is coming, it has a fixed area, fixed pulse wave area. But with the help of this lens, you can focus or defocus the area, right? And based on the focused area, you have got the area available, and since it is focused, area is very, very small. So when you use lens, I think it's a kind of 1 millimeter radius circle, or I would say 1 millimeter semi-major axis ellipse is there, and accordingly, area of the laser beam which is falling at the target becomes very, very small. So the way you can control laser fluence is the area, number one. Number two, at numerator it is the energy. So you can tune energy also. So based on the optimum choice of energy at the numerator and the area at the denominator, you can control over laser fluence. And this laser fluence is critical, and I mean, for a given target, there is a threshold kind of laser fluence. So below this particular laser fluence, let's say I'm saying 1.5 joule per centimeter square. So let's say below 1.5 joule per centimeter square, there will not be any ablation occurring. So that means I have not provided sufficient amount of laser energy to the material. So one has to have optimized laser fluence at the target so that my plasma can be created, right? So that is how we have shown you. It has been shown that based on the spot size that you can focus with the help of this thing, you can control over laser fluence or laser density, right? Uh, Next is wavelength. You know, in my laser, let's say if we are using NDR laser, I am having all possible wavelengths, all four possible wavelengths. Fundamental is 1064, which is in IR range. Then from 1064 to 4 omega, which is 266 nanometer. So we can go from IR to UV. So based on my requirement as well as my technicality, because lambda is very important in absorbing the laser beam, right? So based on which kind of target material you are using, if you are using insulating material, oxide material, you go for UV. If you are going for metallic, you go for IR kind of wavelength. So depending upon target material, one can select wavelength, and yes, it is very, very important process parameter for the growth of thin films, high quality thin films. I don't wish to forget this particular aspect, safety. Not only for PLD, as a teacher, it becomes my own responsibility to take care of my all students who are working in lab. Not only students, my staff who is there in the lab. And you know, since here in this PLD, we have been using high power laser because energy of the laser beam is very, very high. In fundamental mode, if I take NDR laser, it is about 1 joule. And the area, radius of the beam is about, let's say, 4 or 5 centimeters, 5 mm. So energy fluence becomes very, very high. Okay. So since we are using very high power laser and they are class 4 laser, class 4 are the most dangerous lasers which one can deal with. So in PLD, we have been dealing with the lasers which are most dangerous, right? Dangerous in what sense? If you have that laser beam coming to your body, coming to your eye, then it can damage permanently. Okay, so those who are working with PLD, one has to be trained properly. One thing. Second, those who are working with PLD, they had to wear goggles. They are UV filtered goggles, so they will not allow laser beam of that particular wavelength to get into your eye. So without laser goggles, operators, whether it's a student or operator, is not allowed to use PLD. One thing. Second thing is, since I don't know if somebody has, let's say, misaligned the mirror, then there is a possibility that laser beam may reflect to some not to the chamber, it may come to you. So only the trained students and staff should be allowed to work in the lab where PLD is established, PLD is created, right? So if you are casual in operating PLD, then it can damage you, and that damage is very severe. It can be permanent kind of damage. Okay, so one has to work with all possible safety concerns that has been recommended by the laser industry, laser company. Without that, one should not be allowed to work in lab at all. If somebody finds yes, if his rent is working without laser goggle and he is using lasers casually, then he should be debarred permanently. Otherwise, it's a big loss to the staff. So, in fact, I have been trained in an institute where safety had been very important concern, and we were told. I tell you very honestly, we were trained by our supervisors that even if you are working with computers, even if you are sitting in a computational lab, do not sit alone. You must have one more lab partner with you or lab staff. Okay, so that in case of emergency, he can help you. So it has been recommended in my lab, was recommended, can never work alone. Those who are working with experiments, they should never work alone. They should have a group, maybe more than one staff has to be there, and all primary safety concern has to be looked into, right? Even if somebody is working with computation lab, I'm saying, where only computers are there, even then we were told, don't work alone. although sometimes some Israel do work, but it had been recommended many times to do not work, right? And do take care of all safety concerns. In this PLD, safety has to be the prime. Okay, one should not use PLD, one should not operate laser if he or she has not been trained for it. Number two, if he or she is not wearing laser goggles, safety goggles, one should not allow to switch on the laser. Very, very important. Okay. So this is other than my research. So research will keep happening. That's not an issue. But lives are very, very important, right? So that's one thing. That's I think maybe some of the uh, results where how my wavelength affects the surface of the target is shown. So when you take, let's say, high wavelength 1064, I am getting a hill kind of pattern. So here these hills are, high of the hills are very, very sharp. But if I reduce the wavelength, let's say 266 nanometer, then these hills are not very sharp, not very high. So what happens is, if you go for, let's say, 1064, if laser beam is coming to, let's say, at this corner, then in this case the chance of getting bigger particles or splashing become more. Okay, but if you are working with here, then chances of getting bigger particles at the surface is less. So this is for the target, this is for the field. So see, if you are using high wavelength, then the size of bigger particles are more. But if you go for lower wavelength, then surface quality is little better as compared to this. So one can optimize wavelength based on your requirement. If somebody is interested, let's say for some application, my surface roughness is not at all an issue, then I can go for any wavelength, right? But if for some application, certain application, surface roughness is a critical issue, then one has to be very, very careful about it in selecting wavelength. Okay. Similarly, laser fluence, one has to optimize laser fluence based on your congruent and threshold evaporation, threshold fluence. So let's say here we have shown, okay, if you are working with 532 nanometer, for 532 nanometer, if you want to go for congruent deposition, then this is the energy fluence, right? If you are going for 266, this is basically the energy fluence. So maybe 0.45, 0.56, 0.78, 1.34, this is a kind of optimum wavelength, right? So if somebody is working in 266, 355, then this is the region where you can optimize your laser fluence from 0.5 to, let's say, 1.34. But if you're working with 1064 nanometer, then laser fluence has to be much lower, right? So that's how you can do. Other than the parameters I have shown, there are some more parameters. They are again very important, and they also decide quality of film and growth of the film. One more parameter is ambient gas. So when you deposit film, one thing is you first create inert atmosphere. You evacuate the chamber for to high vacuum, let's say 10 power minus 6 millibar, right? Then based on the requirement, let's say if I am working with oxide, so I will create oxygen atmosphere in the chamber. And if I am working with nitrites, I would be creating nitrogen atmosphere in the chamber. So this atmosphere, which we basically use to compensate the loss of oxides or oxygen or nitrogen, is very important. So how much amount of oxygen pressure or nitrogen pressure will be there in the chamber will also decide the quality of film, right? Or quality means whether my material or my film is oxygen deficient or they are of stoichiometry exactly with the same oxygen or not, right? So amount of oxygen partial pressure or nitrogen partial pressure will take care of vacancies of oxygen or nitrogen in the film. And accordingly, they will also play a very important role in deciding a proper phase in the film. One more parameter is target to substrate distance. Yes. So if you place your substrate very close to the substrate, then maybe collision between the plasma and the background gas, my film quality may be affected. Other than that, I think we have shown. I think temperature. I think did I mention temperature here? No. So other than that, there are much more parameters which are controlling film quality a lot. For example, target surface roughness. If my target surface is not smooth, then my surface quality of the film may not be good. Bulk density, if my target is not dense enough, then again my quality of the film may not be good. Repetition rate of the laser beam in per second, how many pulses are coming to the target, that will also decide the quality of the film. Substrate temperature, most important parameter, substrate temperature. If uh, if let's say I am growing film at room temperature, then there is a possibility that my film phase may not, the structural phase may not grow at this temperature. So you need to provide the temperature either during deposition or after deposition. That means either in situ temperature or ex situ temperature. Right. So these are the issues that one should look at. Maybe here we have been showing, I think that's a picture demonstrating how target substrate distance affects the quality of film, how repetition rate. Okay, so you see, if it is 2 hertz, my surface quality is better. If it is 15 hertz, my surface quality is not better. So we need to optimize repetition rate. Repetition rate means number of pulse coming per second to the target, pulse of the laser beam. And here it is a temperature. So sorry, this is the quality of the film. This is unpolished. Sorry, this is unpolished target. Unpolished means you synthesize target by some method. Let's say solid state reaction route. You centered at very high temperature, and the unpolished target was used for the deposition of thin films. So in that case, my quality of film may not be good. But if you polish it, yes, surface quality is improved a bit or up to very good extent. Similarly, the temperature, if you deposit film without giving any temperature to the substrate, there is no growth. But as the temperature is enhanced, then perhaps I started observing proper phase, right? So that's one more parameter. As I said, the temperature helps you in getting proper phase, and which I would say it is a issue with PLD again. It requires high temperature. Here I am saying above 700, we are able to see the proper phase of a material. Okay, so this is how we grow thin films with the help of PLD. I just said thin films, so you can use material of your requirement. For example, if you're working with, let's say, energy-related materials, maybe positive anode, negative, or supercapacitor applications. So for that, there are materials, and I mean, there are devices which are based on it. And for those devices, you can make use of PLD as a tool, and you can make the materials or thin films based on it. Right. I will take some examples also, maybe in the next half of the talk. Next is we have studied that we can make thin films with the help of PLD, but this laser can also be used to synthesize nanoparticles, right? And again, for the synthesis of nanoparticle, you don't need such a big chamber. You just need laser beam, and rest you can grow nanoparticles in a very simple way. I'm just sharing. It's a laser irradiation in liquids, or simply the laser ablation in liquid. We call it, sometimes it is called as LIL or LAL. It is basically way of synthesizing nanoparticles with the help of laser ablation in liquid. So what we do is, we take liquid. In that liquid, we keep some target. Let's say if I'm planning to make nanoparticles of nickel, so I will take nickel here. Or if I wish to make iron, then I will take iron here. Laser beam will come to this iron, and within this liquid, the laser beam will get absorbed by the material, and you will have nanoparticles coming out with the help of this laser material interaction, and they will be getting dissolved in the liquid. And let's say, I'm just taking an example. Let's take you are trying to make nickel nanoparticles in acetone, right? Acetone I took as a liquid, So now what will happen after ablation? My nanoparticles are there in the acetone. So take one drop of acetone and put it on a slide, or let's say on a slide, and what will happen? My acetone will evaporate, and you will have nanoparticles of nickel left thereafter, right? So maybe I'm just suggesting one way, right? So you can make nanoparticles there in the liquid with the help of laser ablation, or you can have nanoparticles independently available with the help of laser ablation. This is one way, and these are the methods. Laser beam is coming, and then it is interacting and making a plasma, and finally you are getting material, the nanoparticles of the material. Let's say here we are saying it is a iron oxide nanoparticles, right? Right. Let's say another same method. Light is coming in and bubble is getting, and then gas phase is coming, and finally you are getting a particles in the laser. There is one more way of doing is laser fragmentation method. So what you do is instead taking target, bulk target, you take, let's say, some particles of higher size or some morphology, and they are dispersed in the material, in the liquid. You shine the laser beam to it. So with the having interaction with the laser beam, these particles will fragment, and you will have photothermal vaporization, Coulomb explosion, and finally you will be getting particles of different morphology coming inside the liquid. So this is one important way. Here we are showing that you can make quantum dots of zinc oxide with the help of this laser, laser irradiation in laser fragmentation in liquid. You take a laser beam, there is a solution in there is a zinc oxide hollow nanospheres in the solution involved, and after having interaction, you are getting quantum dots of zinc oxide. This is the HRT revealing structure of these quantum dots. Okay. In fact, for nickel, you take nickel material, nickel solution in the nickel solution where nickel particles are collided in the solution, and you take laser beam, then you can have quantum, you can have nanostructures of very funny, very interesting shape, which is a double kind of shape. Okay, and very fine quality, very good quality nanoparticles of this shape, where their physical properties like magnetic properties can be tuned, right? So this is one more way. There is one more method within this only. Instead using liquid, you can use furnace. Let's say this is a furnace, and you use, let's say, some target. Here I am taking graphite target. Okay, and laser beam is incident to this target, and it is kept at a temperature. Okay, so with this laser material interaction, plasma will get, and you can generate with the help of plasma. You can prepare, you can synthesize carbon nanotube. Okay, depending upon the conditions. Condition means what is the temperature, what is the distance, how is the laser energy, laser phase. You can create nanotube. It's a very interesting paper where, see, one single nanotube could be prepared with the help of laser ablation in furnace. Very challenging job. Just one nanotube was prepared. Okay, see, it's a 3 nanometer thick CNT, and it has been stretched between two metallic particles from here to here. So it can be used to make a nano device. So system is very simple. You take laser beam and shine it at the target, and you are done with the synthesis of nanoparticles. So there are ways of making nanoparticles. There are ways of making thin films. There had been certain difficulties. I have already discussed that. There are certain beauty, certain good thing about the system, that also I discussed. Okay. So I think I discussed one portion, one segment of my talk where we were talking about pulse laser deposition as a technique or as a tool. If you have any question, I will give a pause at here. I will give you just 1 minute break at here. If you have any question or any query, you can please ask if you want.
Sir, am I audible?
Yes, madam.
Yeah.
Excuse me, sir. Good afternoon. Myself Namrata Saxena. I
Yes,
have
ma'am.
few questions regarding PLD. Is it possible to use PLD on a flexible substrate based on
Yes,
polymer like
madam,
PDMS
I
substrate
already,
like this?
told, yes, I already told it is a, see, if your growth is not at high temperature, then you can use, there is no issue about it. But if the growth requires high temperature, then perhaps your flexible substrates cannot be used in PA. Okay, like plastic you want to use, polymer you want to use, you cannot use in that case. Yes, it is a problem. I will discuss one example where, I mean, particularly for, let's say, one oxide, we require 700 or 800 degrees centigrade temperature, and at such a high temperature your flexible electrodes will not work, will not sustain. In fact, glass substrate will not work, it will diffuse, right? So PLD is a problem for such applications. But in our one of our study, we could reduce this growth temperature of, let's say, 800 to 400 degrees centigrade. If some phase is getting formed at 400 degrees centigrade, and at 400 degrees centigrade your maybe flexible device is able to sustain, then you can do. Otherwise, yes, it's a problem. Madam.
Okay, okay, thanks.
Any other?
Oh. Any other question, please? Sir, take a slight break and then. Yeah.
Maybe just 1 minute break, sir. Maybe
No,
we
no,
will
no,
just.
no.
अभी है सर, थोड़ा समय है, so that I can
वो first time है.
है भी आधा घंटा, तो थोड़ा बात कर लेंगे टॉपिक.
Yeah, 1:30. Yeah.
आधा घंटा है सर.
ठीक है. It depends on you. It is not necessary.
नहीं ठीक है. We will discuss certain examples. 1 or 2 examples I discuss. इनके energy related example I discuss. Thank you.
Briefly, can you explain the facilities available in MNNIT? That would be better for the.
Okay. So since
Department of Physics and others, that is particular. What we are doing. Yeah.
So in the department, we have been working. Most of the faculty members they work in experimental condensed matter physics, in thin films, nanostructural material for different applications like energy storage. Sir is working, sensing applications. Sir is also working in that area. Magnetic storage, magnetic materials. I am working. Semiconductor materials. I am working. So for those who are interested in working for nanostructural materials for different applications, thin films, or maybe theoretical computational study of these such materials, we have sufficient facilities available in the institute, in the department. So in the department, I think we have got facility for the synthesis of nanoparticles using chemical route. Okay, we have got facility for the deposition of thin films using spray pyrolysis. One can use spin coating, yes, you can use. And we have got furnaces for the growth of nanoparticles or the materials. And for characterizations, department has got photoluminescence spectrometer, UV bulb. We have got for sensing. We have got arrangement for gas sensing or other sensing applications. And in addition to the departmental facility, we have got one central facility at MNIT, which is CIR, Center for Interdisciplinary Research. There we have got. We have got two segments, I would say. One is the synthesis lab. Second is the characterization lab. In synthesis lab, we have got PLD, we have got sputtering, we have got thermal evaporation system, we have got electron evaporation system. So spin coater we have got, potential state we have got. These are the, and we have got oxidation reduction furnace available with us. So those who are working, willing to work in that, they are welcome. In addition to synthesis, we have got characterization facilities as well. For characterization, we have got high resolution X-ray diffractometer with thin film attachment, where we can do rocking curve, we can do reciprocal space mapping, we can do theta to theta scan, which is ordinary, right? And then we have got VSM, vibrating sample magnetometer, for magnetic measurements. It is a 3 Tesla superconducting magnet. You can do magnetic measurements like MH, MT at room temperature, and from room temperature to 80 Kelvin, liquid nitrogen, you can do MH and MT. in VSM. We have also got UV visible is there, PL is there, electrochemical analyzer is there, physical quantity measurement system is there, particle size analyzer is there, scanning tunneling microscope is there, scanning electron microscope is there, atomic force microscope is there. For semiconductor, those who are working with semiconducting materials, for them we have got semiconductor parameter analyzer with probe station. So one can study IBCD measurements easily. We have got potential state galvanometer for electrochemical analysis. Okay. So, and I think that's all. We have got sufficient systems for characterization and synthesis. Yes, it is there in CIR.
Excuse me, sir.
Yes, please. May I know what's this?
Yes, Namrata Saxena again. Sir, I want to ask one more question. Sir, is there any general rule that when we increase the annealing temperature of the thin film, suppose we have deposited a ZNO film at a room temperature, and we have annealed different samples at different temperatures. Now, is it there any general rule for roughness relation with temperature, as the roughness every time increases or decreases with temperature,
Uh,
or it depends on the kind of material we are working on?
See, temperature gives you additional energy for the stabilization of phase, right? If you want to grow phase, if you want to grow structure of any material, you need to provide some energy, certain energy, right? So for structural stabilization of particular phase, you need to give some energy. And as far as roughness is concerned, see, in PL, you are asking general. Maybe, I mean, allow me to think a bit, then I'll respond to this question. Maybe coming.
Okay, sir. No.
I will be
No
giving it.
issues.
I will just share this. But particularly, I have not studied temperature versus roughness, because for my applications, I'm not very much concerned about roughness. But those who are working or interested to work with semiconducting devices, their
Yes, sir.
roughness
I am working on semiconductor devices. That's
your
why I am asking this
roughness is very crucial, right? So
question. Yes, sir.
for you, surface roughness has to be very, very good, right? So one has to be very, very careful about surface roughness. Uh, and it depends on the growth, how you are growing. Like in PLD,
Yes,
as I said, there are various things that are supporting surface roughness. Just a surface, as I said, target should be dense. Energy fluence is parameter. But as a function of temperature, I said I'll just answer to your question shortly within a minute. I'll just some rule I'll just think and will let you know just now.
Okay, sir. No issues.
Maybe in coming
Sir,
slide.
one more question.
Please.
Sir, if we want, suppose we want to do shadow masking on some layer, and
Yes.
in that shadow mask, we want to deposit another layer using that shadow mask, and that deposition is done using PLD. Is it
Yes.
possible,
Yes.
or
Yes. Yes.
it
Yes.
would damage the shadow mask?
No. It is possible. You use shadow mask and you make electrodes, different electrodes. It is possible, but one has to mount that mask properly. If it is not properly fixed to the film, then there is a chance that my laser plasma will get in and it may diffuse the electrodes. So
Yes,
shadow,
sir.
yes, it can be done.
Okay. Thank you very much, sir.
Any other question, query that somebody is willing to
Oh,
answer?
now the participants they can ask something here for information also, that it is better to get information.
My talk was little off from what they had been
No, that was very informative. That was very informative.
So it was a kind of informative lecture. I will be discussing some, maybe if I do have some 20-30 minutes time, and I'll discuss one or two applications also. Chala sir, shall I move on?
Yeah.
Okay. So, okay. Now, once again, I think my slide is visible. Is it visible?
Yeah, it is visible. It is visible. It is
Just
visible.
1 minute. Just 1 minute.
Some examples. Yeah.
I'm coming to it, sir. Yes. So I would be taking a few examples for your energy related problems. Okay, some are related to my own research, my own work. Some are related to energy applications. So I will not take much time on it, but I will try to discuss few applications, few very interesting outcome of this PLD, the thin films grown by PLD. So let me talk of one very interesting material, which is ferrite. Ferrite is basically ferrimagnetic material. What is ferrimagnetic? If I talk of ferromagnetic, there is a difference between ferromagnetic and ferrimagnetic. So usually when I talk of magnetic material, it is ferromagnetic. Ferro means magnetic movement of neighboring atoms. They are aligned in aligned parallelly. Okay, within the domain, my magnetic movements are aligned parallelly. One thing, second thing, they are of same magnitude. It's a, I think you might have studied in graduation or PG. Okay, my magnetic moment of ferromagnetic materials, they are aligned parallel and they are of same magnitude. So this is my ferromagnetic. Similarly, if I talk of anti-ferromagnetic material, maybe lecture now. Secondly, anti-ferromagnetic, when I talk of anti-ferromagnetic materials, means I am having magnetic moments aligned anti-parallel. So magnetic moments are aligned anti-parallel and they are of same magnitude. So resultant magnetic moment will turn out to be 0. Now, if I talk of ferrimagnetic materials, it is a, I would say it's a case of anti-ferromagnetic materials where my magnetic moments of neighboring atoms, they are aligned anti-parallel. So alignment is anti-parallel, remember, but their amplitude is not same. So resultant will be some kind of magnetization. And this is one thing. Secondly, these materials, they have very high resistivity, very high. Almost they are basically oxides, and they have very high resistivity, and thereby they don't give any. I mean, there are very low losses when you apply, when you magnetize them at very high frequency fields. For example, radio frequency fields. So other than their other applications, these materials can be used for communication purposes, right? For radar communication, for high frequency communication, you can use these materials because they give very low loss when you magnetize them in high field, right? Basically, they are of two type, I would say. I mean, structurally, there are two divisions. One is cubic, second hexagonal. Within cubic, there are two, spinel and garnet. Hexagonal, they have got hexagonal structure. So let me just discuss one small example. Let's say if I'm talking of cubical ferrite, spinel ferrite. So basically, spinel ferrite have got this formula, MFe2O4, or I would say MoFe2O3, where M is basically a divalent metal ion. You can choose any divalent metal, manganese, nickel, zinc, iron, cobalt, okay, or combination of these two. So resultant will be my spinel ferrite. And here in spinel ferrite, you have got two type of lattices, interstices. This is a tetrahedra. I am having one metal ion here, and there are 4 oxygen here. So this is forming tetrahedra. And there is one more here, which is giving you octahedral. So there are two sides. One is tetrahedral side, second is octahedral side, and these are the number of sites available in system. And based on how my this divalent ion and this iron ion, ferric ion, they are distributed, you have got two types, three types I would say. One is normal, second is spin inverse, and there is one more which is mixed spinel, where there is a mixing of both. So what I am saying, normal means my entire divalent metal ion, it is going to A side. So let's say if I take zinc ferrite, right? So zinc ferrite, zinc is +2. So this zinc +2 is going to your A side, and my Fe, which is in 3+ state, they are going to B side. So it is a case of normal spinel. But if reverse is happening, reverse means half of ferric ion is going to A side and my divalent metal ion is coming to B side, then it's a case of inverse spinel. And accordingly, based on the arrangement of magnetic moments, the system will give you net value of magnetization. For example, I am taking a case of spinel, normal spinel, which is zinc ferrite. So if I take a case of normal spinel, it's a zinc ferrite. So in zinc, zinc is in 2+ state. 2+ means it has D zeroness, right? All D subcells are filled because the 4s2 electron is out. So here all electrons are in paired state. So if I look at zinc +2, which is in A side, so here it is, this zinc is in A side. So all zinc divalent atoms, they are in A side, right? If that is the case, then zinc 2+ will not contribute to magnetization because it has all unpaired, there is no unpaired electron available, so it will give you zero magnetic moment. But if I look at iron, Fe, there are two ferric ions and both are going to be there in octahedral site here. So it is a case where my ferric ions are in octahedral site. So out of these two, one ferric ion, because one ferric ion has got how many unpaired electrons? Fe 3+ means 4s2 is out and 3d from 3d6 one electron is also out. So you have got 5 unpaired electrons in D subshell, right? So those 5 unpaired electrons in D subshell will give you 5 Bohr magneton magnetic moment, right? So one ferric ion is giving you 5 Bohr magneton magnetic moment. Second is giving you same, but since it is a case of ferrimagnetic moment where atomic arrangements are anti-parallel, now in this particular case, magnetic moment of this and magnetic moment of this is same, so it will cancel out. So when zinc oxide goes to this structure, as a whole, it doesn't give you any magnetic moment, right? So it has a zero magnetic moment, and its Néel temperature is very low, about 10 Kelvin. So at room temperature, this material does not show any magnetic moment. So what I'm saying is, zinc ferrite is a very simple, very well-known spinel ferrite, showing spinel structure, right? But it is non-magnetic. I'm using word non-magnetic, but it does not show any hysteresis loop when you try to record magnetization at room temperature. But is it possible to change arrangement of these ferric ions? If let's say some of my ferric ion goes from here to here, let's say this ferric ion can go from here to here. So I'm looking at, is it possible to have zinc ferrite in inverse spinel structure? So in bulk, zinc ferrite is a kind of normal spinel. So when I say zinc ferrite, it is a normal spinel, it has zero. But if I can somehow bring this ferric ion from B to A side and a portion of zinc ion from A to B side, then perhaps I may have some kind of unpaired magnetic moments or uncancelled magnetic moment, giving you resultant value of magnetization. That's how I'm saying. So what I'm saying is, instead having ferric all ferric moments at here, you can have some sort of ferric moment in B side and zinc at here. So if that happens, then you will get some kind of unpaired magnetic moments available, and if that happens, then the resultant will be some magnetization in some magnetization in zinc oxide compound. And it is a situation where my ferric ion is going from entirely B side to A side. It means my situation is going from normal to inverse. So see, here I am getting iron in tetrahedral as well as iron in octahedral, and my zinc is going to octahedral side. So my uh, zinc ferrite can also be there in the inverse spinel structure. If that happens, then my magnetic movement of the system can be. So what we did is we synthesized zinc ferrite thin films. We are calling them nanocrystalline thin films, and two series were prepared with the PLD only. One was in oxygen, where the oxygen pressure was 0.16 millibar. Second was in vacuum, where no oxygen was. It was evacuated to 10 power minus 5 millibar. So we are calling them ZF PLD1, ZF PLD2. So, you know, that's how we have prepared the target. It was prepared by using soil state reaction route, sintered at very high temperature of 1300. Now, if you see this, my XRD gives you, it is XRD of zinc ferrite films grown in oxygen at different temperatures. So it's a polycrystalline phase of single phase of zinc ferrite films. Similarly, we have got XRD for other series also, and based on XRD, we calculated lattice parameter as well as particle size. So you know, grain size or crystallite size, I would say. So when we study zinc ferrite thin films with grown in oxygen and grown in vacuum. So this is grown in vacuum. We observed one very interesting observation. See, films grown in oxygen, they are of less particle size, grain size, and their lattice parameter was almost same. It was 8.41. But when we grow it these films in vacuum, then situation was little changed. We have got higher grain size and my particle size was lower. So what we did is we tried to calculate rearrangement of atoms and these ferric ions and zinc ions from A to B or B to A site, and then we tried to find out whether this the value of lattice parameter which we are observing is matching with the redistribution of these ferric ions, and we got yes, it is the case. Now, interesting problem is this: although zinc ferrite is diamagnetic, it is paramagnetic at room temperature in bulk, but when we synthesized in thin film form at different temperature, this is the film in oxygen, this is a film in inert atmosphere. So in inert atmosphere, you see, we have got very good hysteresis loop. Okay, it shows very good quality zinc ferrite films with magnetization. We reported for the first time, okay, this magnetization, and that is how it was following the temperature and it was following the grain size. So we could explain observation of this magnetic movement with the help of redistribution of redistribution of zinc ion and ferric ions from A to B or B to A side, as well as with the grain size. Okay, so, and you know, when this ferric ion is going from B to A side, this should be theoretical value of lattice parameter. We were matching this value of lattice parameter experimentally as well. So we could theoretically and experimentally we could establish yes, there is a cationic distribution going on within the zinc ferrite, and accordingly, when you synthesize zinc ferrite in thin film form at different conditions, these film become magnetic. So it was very interesting observation. A material which is non-magnetic in bulk, it is magnetic in thin film form. And yes, that was very good report. Now, one can also look at these zinc ferrite thin films. In fact, silver has been doped. So these zinc ferrite has also been recommended for the new anode materials for lithium-ion batteries. So now, what had happened? These nanocrystalline zinc ferrite films or films were prepared with the help of PLD, and you know, and they were prepared on substrate like stainless steel. Okay, so the bottom curve is zinc ferrite films grown at assess substrates, analysis substrate, and it shows polycrystalline growth of zinc ferrite as we were getting. And you know, growth temperature was 600 for all. These are some more zinc ferrite films doped with different amount of silver into it, and they are lithiated zinc ferrite films. So I would be just talking about what is happening to zinc ferrite. See, I told my area is not energy storage of these materials, but yes, you can use PLD, you can use these materials for energy storage applications. So you know, zinc ferrite films, they were used to study electrochemical analysis, and they used electrochemical cells, and that too in dry argon atmosphere. And this is the setup that they did. Okay, zinc ferrite films were used as positive electrode, and your high purity lithium metal foil that was used as negative electrode, and charge discharge mechanism was studied in this. So if you look at this, you know, this is the CV curve of zinc ferrite films in first 3 cycles. Here you could see that these 1, 2, 3 are basically representing yeah, these are basically suggesting certain features. Let's say at B and at C, what exactly is happening. You know, if I talk of cycles, let's say if I look at cycle number 1 and if I look at cycle number 3, when I go from cycle 1 to cycle 3, then this loop has a significant change, right? There's a significant difference. So from 1 cycle to 3rd cycle, my loop is getting changed. So that means first cycle is basically showing reduction in peak, right? So when I go from 1 to 2nd cycle or 2nd to 3rd cycle, then these peaks, let's say this B and C peak, they are either shifting towards higher voltage or they are getting diminished, right? So when I'm saying what is this B or C peak, they may be due to reduction or oxidation of ferric ion in my zinc ferrite. Now, if I look at this voltage composition curve, yes, these are different curves for different composition, right? Okay, so here this N, D, and C, they are representing 1, 2, 3. They are representing nth number of charge and discharge. This is charge. This is discharge. So for a different composition of lithium in zinc ferrite, this charge and discharge curve is also shown. And yes, one can easily see that zinc ferrite films can also be made useful for my energy storage application. Not only thin films of zinc ferrite, one can make use of nanoparticles with different morphology. For example, zinc, the same material I'm talking about, zinc ferrite. Thin film form, it is getting this kind of reversible capacity 434 over 100 cycles. Okay, but if you go from thin films to, let's say, nanoparticles, fibers, octagons, nanorods, cubic nanoparticles, hollow sphere, hollow microspheres, nanosphere, then correspondingly my reversible capacity is increased, right? 434 to, if I'm talking about hollow nanosphere, then it is going 1101 over 120 cycle. So my electrochemical performance of this material is very enhanced. So we need to, one can look at this issue of zinc ferrite nanostructures for films. Similarly, you can also look at lithium nickel manganese oxide, which is LMNO, very common cathode material, right? And again, these are also prepared by PLD. One can prepare LMO lithium-rich film by PLD, and that's how my XRD shows that these are polycrystalline samples. And again, you can study charge discharge of these materials. And these are different charge discharging curves. And you know, for these samples, my discharge capacities was almost stable. It was found slightly decreased over 100 cycles. If you go for more than 100 cycles, then my charge discharge capacity was going down. Okay, so this has been studied. LMO film shows some combination of high rate capacity or some other factors, but I don't know whether it can be used as a as a good candidate for long-lasting cathode material or not. One has to study more on this. There are a few more applications like you can use PLD for positive electrodes like lithium cobalt oxide. It's a very famous positive electrode material. So one can prepare thin films of lithium cobaltate like cobalt oxide. Okay. Not only this, there are many such positive electrode materials wherein V2O5. Many, I would say there are a number of V2O5, MnO2, LM, lithium manganese oxide, LMN2O4. So various materials are available for positive electrodes, and you can synthesize thin films of all, and there is a enhanced properties available. So here, if you see, I'm just taking an example. Here, thin films of LCO was prepared with the help of PLD. See, it's a very interesting. It is a off-axis. My substrate was placed, not maybe in my earlier slide I have shown it is at 120 degree, but here it is at 90 degree. It's a off-axis deposition, and yes, you could see growth of LCO at comparatively lower temperature also, 400 and 850 both. And here, you know, MPS, they are basically the impurity, I would say, Fe3O4 phase at room temperature, and S is representing substrate peak, and maybe platinum is also coming from some impurity, which is maybe from the stage. But yes, you can grow high quality LCO films. And they also show electrochemical properties. So these are showing electrochemical properties, and this has been studied for different hours, for 16 hours, and this is done for 9 days. And there's a very sharp observation here. Okay. Similarly, one can also give some more temperatures. Just a second. सर मैं लेक्चर बताएं सर मैं हाँ बोलिए सर हाँ एक लेक्चर में बस 10 मिनट में खत्म करते हैं ठीक है ठीक so again these films are grown LCO, and you can see that yes, there is a sorry, there was a network issue. Okay, not only positive, you can also look at negative electrode materials. It's a very common example. Titanium oxide is a very common example. It has various phases available: rutile anodase, rutile, TiO2B, R, H, second and third phase. Among them, I think one can look at rutile anodase phase, which are reported intensively for anode material of for the lithium-ion batteries. Right, this is a possible electrochemical reaction that can be described or used to describe the electrochemical studies. Now, if I just see to it, one can easily grow or control the rutile or anodase phase in titanium oxide based on my process parameters. Here, you know, thin films of titanium oxide was prepared, and when it is deposited in vacuum, it has rutile phase. But if it is deposited in presence of oxygen, it gives you anodase phase. So one can easily tune the desired phase just by controlling over oxygen parameter, oxygen atmosphere in the chamber. In addition, it can also be controlled by having different temperatures also. So, you know, for let's say here again, this TiO2 films were prepared at 473 Kelvin. It shows anatase. Sorry, it was.
That's all.
Sir.
May I request you to summarize the things?
So I'll be summarizing. I think that's all. I think
Oh.
my so I mean we can have various materials. TiO2 have shown. In fact, nickel ferrite is also very good material for the lithium-ion batteries as electrode material, right? There also one can see a very good quality discharge capacity has been observed in nickel zinc ferrite. So I mean now I'm skipping because it will go on. So that's I mean this will go on. Just one more slide I wish to show. I think that would be important. You know, yes, let us look at this also. One or two slides I will be looking at. I just said in laser ablation, my oxides are grown at high temperature, okay, more than 700. So can we minimize, can we overcome this issue? And for that, what we did is, we just did an experiment. We used magnet, a kind of permanent magnet between target and substrate. So this we called as magnetic assisted laser ablation. And here we have grown strontium ruthenium oxide films at STO. And by applying magnetic field or by varying magnetic field, yes, this growth temperature, which was 800, it was reduced to 400 degrees centigrade, right? And crystal structure of the film was very good. And not only crystal structure, I mean, its transport properties was close to bulk. Okay. In addition, we could also observe that coercivity was also tuning. So one can tune not only the I mean, temperature, we can also tune coercivity of the material if we apply I mean variable magnetic field at in between target and substrate. So this was one work that has helped us to reduce the growth temperature, which was usually very high in case of PLD, right? So one can look at this aspect also. In PLD, one can easily, not easily, but one can lower down the growth temperature if somebody is interested. I think Madam was asking about it. I think that's all from my end. I wish to acknowledge my mentors, my supervisors, my collaborators, my students. I wish to acknowledge Professor Prashad, D.S. Mishra, Professor Venkatramani from IIT Bombay. They had been my PhD supervisors. Okay. And I also acknowledge Professor J.H. Jung from Inha University in Seoul, South Korea. And Professor Namjang Gur, I forgot to mention his name, but Professor Namjang Gur is also acknowledged. My colleague, Dr. Murtaza Bora, he is in Mahendra Ecole these days. So I acknowledge the contribution of Dr. Murtaza Bora for this talk. And I wish to acknowledge GST, CSAR, TCube3, and MNIT Allahabad for having experimental facilities at MNIT. Okay, and CIR MNIT because we have been using almost all facilities at CIR, so it is greatly acknowledged. And lastly, my students. Although I'm saying PhD students, but there are some more students associated, those who are not in PhD. Contribution of those students are also acknowledged. I think with this, I'll thank you. Thank you very, very much to all of you for listening my informative lecture on pulse laser deposition. I discussed, although I tried to discuss some applications related to your area. I don't know how much justice I could do. But with this, thank you so much. Thank you.
Yeah, that I should add a line here that you never forget to acknowledge your supervisors. That's really very interesting, sir.
So wherever I will be because of them only, sir. So